Hello everyone, welcome to Module 4, Lesson 4 of Mastering Ethereum. Today we are diving into strategies for reducing gas usage in Ethereum smart contracts. Think of gas in Ethereum like fuel for your car. Just as fuel powers your car, gas powers your transactions on the Ethereum network. Our goal today is to learn how to make our car more fuel efficient. Optimizing gas usage in Ethereum smart contract is crucial for building efficient and cost-effective decentralized applications. High gas cost can deter users and limit DApp adoption. By optimizing gas usage, DApps not only become more cost-effective for users but also more performant and responsive, providing a smoother experience. Let us now look into some techniques to optimize our gas usage and write smart contracts efficiently. To reduce gas usage, it's crucial to minimize the number of storage write and read operations in your Ethereum smart contract. Instead of writing data to storage every time it's needed, try to perform calculations and updates in memory first. Only write the final results to the storage when absolutely necessary. This can involve caching intermediate values. Basically, it means storing temporary results or calculations during the execution of a program or smart contract for later use. Batching updates or using more efficient data structures. By optimizing your use of storage, you can substantially reduce the overall gas requirements of your smart contract functions. Imagine writing a draft on a whiteboard, erasing mistakes as you go, and only saving the final version on paper. By doing operations in memory first and writing to the storage selectively, we save on ink, which is the gas cost. Let us now look into an example for minimizing storage writes. This Solidity smart contract optimized storage showcases an optimized approach to minimizing storage writes in Ethereum contracts. Let's break it down. The contract declares a state variable stored data of UN256 type, which is publicly accessible due to the use of public visibility modifier. The set function is defined as public function, enabling it to be called externally. It takes a UN256 parameter x. Within the set function, there's a conditional check if x not equal to stored data. This check ensures that the new value x is different from the current value of the stored data before proceeding with any updates. If the condition evaluates to be true, meaning x is indeed different from the current stored data, the value of stored data is updated to x using the assignment statement stored data equal to x. This contract demonstrates an effective method for minimizing storage writes by only updating the storage variable when a new value is different from the current one. This conditional check helps in reducing unnecessary and costly storage operations, contributing to improved gas efficiency in Ethereum smart contracts. Using efficient data structure is crucial for optimizing gas usage. Some of the examples include prefer mappings over arrays. Mappings allow you to access specific elements directly without the need to iterate through the entire data structure, making them more gas efficient than arrays for most use cases. Mappings in Ethereum are like having a direct address for your friend's house, while arrays are like list of houses you need to go through one by one to find your friend's place. Mappings allow direct access, making them faster and more gas efficient. Utilizing structs and enums. Grouping related data elements into structs and using enums to represent a finite set of options can help you minimize the amount of data stored in your contract, reducing gas costs. Think of structs as neatly organized drawer containing several related items and enums as specific type of item in that drawer. Both help in organizing your data more efficiently, minimizing storage need, and reducing gas cost. Optimize data organization. Carefully consider how you structure and organize your data to minimize redundancy and unnecessary storage operations. This can significantly improve the gas efficiency of your smart contract functions. Imagine you have a cluttered room where you can't find anything easily. Now picture a well organized room where everything has its place. Optimizing your data organization and contract is like cleaning up the room, reducing redundancy and unnecessary storage operations, thus saving gas. Let us now look into an example of using mappings over array. The efficient mapping contract exemplifies the utilization of mapping for efficient data storage in Ethereum smart contract. So let's break it down. The contract includes a state variable balances, which is defined as a mapping with address keys and UN256 values. This mapping is intended to store the balances associated with different account addresses. The update balance function is a public function allowing anyone to update balance associated with a specific account. It takes two parameters, account of type address and amount of type UN256. representing the account address and the new balance amount, respectively. Within the function, the balances mapping is used to set the balance for the given account to the specified amount. In summary, this contract provides a straightforward and gas efficient way to update account balances using a mapping, allowing direct access and manipulation of specific element without needing to iterate through an entire data structure, thereby minimizing gas usage. Another effective strategy for reducing gas usage in Ethereum smart contracts is batch processing. By grouping multiple operations into a single transaction, you can take advantage of the reduced overhead cost associated with each individual transaction. This approach can be significantly more gas efficient than executing each operation separately. When you perform multiple updates or changes to your contract state within a single function call, the gas costs are often lower than executing those same updates across multiple transactions. This is because the fixed cost of transaction fees, such as cost to include the transaction in the block, are amortized across the entire batch of operations. By batching your contract's logic, you can minimize the overall gas consumption and provide a more cost-effective solution for your users. Batch processing can be likened to doing all your weekly grocery shopping in one trip instead of going to the store multiple times a day. By grouping operations together, we reduce repeated costs, making the process more gas efficient. Let us now look into an example of batch processing. The batch processing smart contract highlights a method for reducing gas usage in Ethereum smart contracts through batch processing. Let's break down the components of this contract. The contract includes the state variable balances, which is defined as a mapping with address keys and UN256 values. This mapping is designed to store the balances associated with different account addresses. The batch update function is implemented as a public function allowing external calls to initiate batch updates to multiple account balances simultaneously. It accepts two arrays as parameters, accounts and amounts, both declared as memory arrays to store data for the duration of the function call. The function begins with a requirement check ensuring that the accounts and amounts array are of equal length, maintaining a one-to-one correspondence between account addresses and their respective balance updates. Subsequently, the function iterates through the accounts array and updates the corresponding balances in the balances mapping with the provided amounts. The batch processing approach showcased in this contract aims to reduce gas consumption by grouping multiple state updates into a single function call. By doing so, the overhead costs associated with individual transactions can be minimized, resulting in a more gas efficient solution for users interacting with the smart contract. Function modifiers in Solidity are special functions that can modify the behavior of other functions. They are often used to add custom checks or conditions to functions without duplicating code. Modifiers are applied to functions using the modifier keyword. By utilizing modifiers, you can enhance the security and efficiency and readability of your smart contract. Optimal use of function modifiers involves embedding necessary logic directly within the function body whenever feasible, instead of relying on separate modifier functions. Inlining checks and modifiers eliminates the additional function call overhead, effectively reducing gas cost by streamlining the contract's execution. Another key strategy is to consolidate common checks across multiple functions. Instead of duplicating the same verification logic in different functions, performing the check once and using a modifier to apply it across multiple functions can help in avoiding unnecessary redundancy and optimizing gas usage. Let us now look into an example of optimizing modifiers. In the optimized modifiers contract, an optimized function modifier named onlyOwner is defined to ensure that only the contract owner can execute certain sensitive functions. Let's look into its breakdown. The contract includes a public state variable owner of type address. This variable stores the address of the contract owner. The onlyOwner modifier is employed to restrict access to specific functions to only the contract owner. Within the modifier, a require statement is used to verify that message.sender matches the owner address stored in the contract. If the condition is not met, an error message is provided. The underscore denotes the location where the modified function's code will be inserted. In this case, it indicates that the setOwner function will be executed if the owner validation check passes. The setOwner function allows for updating the contract owner's address. By specifying public only owner in the function declaration, it enforces that only the owner, as defined by the only owner modifier, can change the owner address to a new value. This contract is structured to provide secure access control by restricting modifications of the owner state variable to only the designated contract owner, thereby ensuring the integrity of the owner related operations within the smart contract. By embedding the ownership check directly within the modifier, unnecessary function calls are avoided, leading to improved gas efficiency in the contract functions. To optimize gas usage in your Ethereum smart contract, it's crucial to avoid performing unnecessary computations within your contract function. By pre-computing values off-chain and passing them as parameters, you can reduce the amount of on-chain processing required. Simplifying complex calculations by breaking them down into more efficient steps can substantially decrease the overall gas consumption of your smart contract. Imagine solving a math problem by breaking it down into simpler steps on paper first before using a calculator for the final result. By pre-computing values off-chain, we reduce complex on-chain calculations, thus saving gas. Here is an example of simplifying calculations to reduce gas usage. In the simplified calculations contract, the calculate function showcases the concept of simplifying complex calculations in an Ethereum smart contract to reduce gas usage. Let's break it down. The calculate function accepts two input parameters A and B of type UN256. It is defined with the pure modifier, indicating that it does not modify the contract state and does not read the contract state either. Within the function, the product of A and B is computed, and the result is divided by 2. This calculation, while simplistic in this demonstration, may represent a more complex operation in the real-world scenario. The example emphasizes the practice of pre-computing values off-chain and passing them as parameters to the contract function. By pre-computing intermediate values off-chain and passing them as input, the on-chain processing can be streamlined and leading to significant gas savings for users interacting with the decentralized application. This example illustrates how simplifying complex calculations and pre-computing values off-chain can lead to more efficient on-chain gas usage in Ethereum smart contracts. By breaking down computations into more efficient steps and leveraging pre-computation where possible, the gas required for contract execution can be substantially reduced. When developing Ethereum smart contracts, it's important to be judicious in your use of external calls to other contracts. While these calls can be necessary for certain functionalities, they can also incur significant gas costs, negatively impacting the overall efficiency of your decentralized application. Aim to minimize the number of external calls within your contract functions. Each additional call adds overhead and complexity, increasing the gas requirements for your users. When multiple external calls are required, consider batching them together into a single function execution. This can help amortize the fixed cost associated with each call, reducing the overall gas usage. For operations that don't require changes to your contract state, use internal functions instead of external calls. Internal functions are generally less expensive and can help streamline your contract's logic. Think of making external calls like ordering takeout from multiple restaurants. Doing it individually for each meal adds delivery charges every time. Instead, if you order all the meals at once, you can save on multiple delivery fees akin to reducing gas usage by batching external calls. Let us now look into an example of using efficient external calls for reducing gas usage. In the efficient external calls contract, the concept of efficient external contract interactions and batch processing is demonstrated. Let's break it down. The contract starts with the definition of an interface external contract that declares a function update data which takes a UN256 data parameter. Interfaces are used to establish communication standards between different contracts. The contract includes a state variable external contract of the type external contract. This variable represents an external contract that complies with the external contract interface. The batch update function is a public function that accepts an array of UN256 values called data as parameter. Within the function, there is a loop that iterates to the data array. For each element in the array, the function calls the update data function of the external contract instance, passing the value at index I. By batching multiple calls to the update data function of external contract into a single function call, The gas consumption is reduced compared to making individual calls. This batching strategy helps amortize the fixed cost associated with each external call, resulting in more gas efficient solution that benefits users interacting with the decentralized application. In summary, the efficient external calls contract illustrates the optimization of gas usage by grouping multiple updates to an external contract within a single function call, showcasing a more efficient approach for interacting with external contracts on the Ethereum blockchain. Event logging is a critical aspect of Ethereum smart contract development, and it's important to use it effectively to minimize gas consumption and optimize the efficiency of your decentralized applications. Event emissions are not free, and emitting event incurs a certain amount of gas cost. Therefore, employing event logging judiciously is essential for minimizing unnecessary gas usage. Events should capture important state changes and record key transaction details relevant to your DApp's functionality. By focusing on logging critical information, you avoid emitting events unnecessarily, which can impact gas efficiency. This efficient event logging contract showcases an efficient approach to event logging within an Ethereum smart contract. Let's break it down. The contract contains an event named data updated, declared using the event keyword. This event captures the important details of data updates, including the user's address, the old value of data, and the new value being set. The contract includes a public state variable data of type UN256. This variable represents the value that is being updated. The update data function is a public function that allows the update of data state variable. Within the function, the data updated event is emitted using the emit keyword, capturing three parameters: message.sender, the address of the user initiating the update; data, which is the old value of the data being updated; new value, which is the new value being set for the data. Subsequently, the data state variable is updated to the new value provided. By emitting the data updated event when the data state variable is updated, the contract provides valuable context for subscribers of the event without incurring unnecessary gas costs. The level of detail captured by the event enhances the user experience and transparency of the contract state changes, contributing to a more informative and efficient decentralized application. Leveraging off-chain computation in Ethereum smart contract involves utilizing external processes to handle resource-intensive calculations, data analysis, or complex algorithms. By performing these computations off-chain and passing the results as parameters to an on-chain function, the smart contract focuses on essential state updates and transaction management, enhancing gas efficiency and optimizing user experience. This strategy reduces the burden on the Ethereum virtual machine by delegating computationally heavy tasks to external systems, streamlining on chain operations, and ultimately decreasing gas usage for decentralized applications. Let us now look into an example of off chain computation. In this smart contract named off chain computation, the contract includes a state variable named result, which is publicly accessible. State variables store values on the blockchain and can be read by anyone. This contract contains a function called storeResult that takes a single parameter computed result of data type UN256. The storeResult function is publicly accessible, meaning anyone can call this function. Inside the function, the computed result parameter is assigned to the result state variable. This essentially stores the computed result in the smart contract state. This function is called after the off-chain computation has been completed, with the final result provided as a parameter. By separating the computation from the on-chain logic, the contract can avoid the high gas costs associated with performing complex calculations directly within the EVM. Let us now conclude this lecture with a short summary. There are several effective strategies to reduce gas usage when developing smart contracts on Ethereum blockchain. By optimizing your contract's design and leveraging off-chain resources, you can significantly lower the overall gas cost for users of your decentralized application. Key techniques include minimizing storage operations, using efficient data structures, implementing batch processing, optimizing function modifiers, and avoiding unnecessary computation. Before we wrap up, here are some questions to consider. What are some additional strategies you can think of to reduce gas usage in your Ethereum smart contracts? How can you apply these optimization techniques to improve the efficiency of your current decentralized applications? Share your thoughts and questions in the discussions forum on the Discord, as the Ethereum community is always eager to learn from one another's experience. We'll see you soon next time for more insights on building gas efficient blockchain solution. Thank you and have a nice day.